If you only watch the golf club, could you tell if she hit the ball? Can you tell if it's a hit or a strike? The action is too fast for us to see, even in slow motion. But if you tracked and carefully measured the speed, there would be an impact or jolt that would show a momentary deceleration the very instant the ball was hit. It doesn't matter if the motion is horizontal or falling like this hammer. Whatever hits a stationary solid object must experience some jolt the instant it hits. It also doesn't matter what angle it hits the object, or if the object is crushed into smaller pieces. The speed of the object doing the hitting must momentarily decelerate in accordance with the laws of momentum. Conservation of momentum is a fundamental law of physics. So what do the fundamental laws of physics have to do with the events of 9/11? Everything. Most people don't realize that the Twin Towers did not experience any jolts as they fell. Careful measurements, such as this one by David Chandler, clearly indicates that the velocity of the roof of the towers uniformly sped up. How can this be? How can the roof of the towers uniformly accelerate with no jolts if it hit or crushed the undamaged structure below? The National Institute of Standards and Technology, NIST or NIST, was tasked with investigating the event. They conducted some experiments, but NIST did not use them because the results did not support a fire-induced gravity collapse. Instead, they resorted to a computer model to prove their desired result, but will not release their model data for verification. They stopped their study the moment collapse began, simply stating global collapse ensued. In other words, they just assumed that collapse was inevitable. But in science, one needs to be very careful when making such bold assumptions. Instead, NIST refers to the work of Professor Bazant and others with their mathematical collapse analysis. To explain the energy needed, their hypothesis relies on the notion that the upper block of floors physically crushed the lower floors into dust. They claim the upper, smaller block of the towers crushed the larger, lower block down to the ground, and then the upper block finally crushed itself. In addition, they said that the crush down and crush up cannot occur simultaneously. They say we simply cannot see this falling block behind all the dust. But independent physicists and engineers have refuted the official hypothesis with their own research papers. They point out that there is no deceleration or jolt, and any structure that is dropped in a larger structure would destroy itself before it could destroy all the lower structure. Therefore, the towers could not have collapsed due to gravity alone. Newton's third law of motion says that for every action there is an opposite but equal reaction. So any force imparted by a falling block striking a lower structure must also impart the same force on the upper block. What the independent scientists are really saying is that an additional force, such as explosive, must have removed the supporting structure, allowing the roof to constantly speed up so as not to experience any jolts, and providing the energy needed to destroy the structure below. Obviously, both hypotheses cannot be correct, so how can we tell who is not correct? By conducting some experiments, the arbitrator of opposing hypotheses. Richard Feynman was a brilliant physicist and a member on the panel that investigated the Challenger disaster, who conducted a simple experiment using ice water to demonstrate the effect of temperature on a piece of the shuttle's seal. He said, "It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. So let's observe some simple experiments to help resolve this conflict." Both towers held the upper blocks of floors for about 1 hour after the planes hit, meaning the total supporting force must be equal to the downward weight of the floors. The goal of the first experiment is to see if there is a deceleration by a falling body by any structure that once supported the static weight. A wood block was gently wedged so that it just barely held the upper block in the static condition. Raising the block and dropping it, you can clearly see a jolt as the upper block hits the lower. The goals of the following experiments are: is there a jolt when an upper structure impacts a lower structure, or will the falling part uniformly accelerate? Can the upper structure destroy a lower structure without destroying itself in the process? Or is the crush down of the lower part simultaneous with the crush up of the upper part, contrary to the official hypothesis. I constructed a rail system in order to guide a falling hollow concrete block onto a stack of 4 similar concrete blocks. The concrete block was raised to the 12-foot mark, equivalent to the floor spacing on the twin towers, and let go. Just like the towers, the falling block did not hit the lower block squarely, but unlike the towers, the falling block obviously experienced a jolt after it hit the lower stack. In addition, both the falling block and the top block of the stack were destroyed virtually simultaneously in accordance with Newton's third law. However, it did not destroy the underlying supporting blocks. The test was repeated with the same blocks, only this time the holes in the blocks were alternated to see if a change in the support structure would make any difference. Similar results were observed. Finally, some very small weak blocks were used. The results were identical, however, due to the lack of support from the guide rails, the stack tipped over, but after they yielded the same results. The next 3 experiments are real-world examples intended to see if indeed, as NIST simply assumed, collapse was inevitable. Will collapse of these structures continue to accelerate, and is collapse really inevitable? Based on these 3 real-world examples, an accelerating straight-down collapse of the structures certainly was not inevitable. In Part 2, we will compare a natural gravity building collapse with a known controlled demolition and show how, with careful measurements, you can tell the difference.